Good morning. I want to welcome all of you to our Ultrasound Basics Seminar presented by Conquest Imaging. My name is Max Morey and I'll be facilitating the discussion this morning. And before we begin, again, I'd like to thank you for attending and also invite all of you to view our training calendar for 2016 and 2017 for all the various ultrasound classes that we present. We teach ultrasound basics, ultrasound DICOM, and all the various makes and models. So please, if you have any need for ultrasound training, please look to Conquest Imaging, as we have the best training in the industry. So I want to launch into ultrasound basics. This course was designed just as an introduction to give people a basic understanding of how ultrasound is created, how it's used, and the basic building blocks for ultrasound systems. And at the very end of this presentation, we will be having a short Q&A. So if you have any questions, you can use the chat box on the GoToWebinar dashboard and send questions over, and I'll be happy to answer them. And also, my email address is on this cover page, and it will be at the end as well. If you have any questions or would like to talk to me live, please email me, and I'll be happy to get back to you. So what we're going to be talking about is ultrasound basics, ultrasound types, and then we'll go into the basic building blocks of diagnostic ultrasound systems. So by the end of this presentation, you have a basic understanding of ultrasound principles. We'll talk about ultrasound transducer types and their uses. We'll talk a little bit about ultrasound physics and the trade-offs with regards to image quality and resolution, different imaging modes, the basic building blocks of any ultrasound system, and be fairly familiar with different systems and their intended use. So as part of the introduction to ultrasound, we'll talk about what is ultrasound, sound types by frequency, the piezoelectric effect, ultrasound transducers, tissue interactions, and image quality. So what is ultrasound? Ultrasound is a sound wave with a frequency higher than 20,000 hertz. 20,000 hertz is the upper range of human hearing. So sound is essentially a mechanical longitudinal pressure wave that travels through a certain medium. In fact, on ultrasound systems, the vast majority of ultrasound systems have a dashboard that shows how much mechanical index, or MI, that we're putting into the human body, and that's important for safety reasons. What is the average speed of ultrasound waves in human tissue? Where this becomes important is when we look at frame rates, or how fast an ultrasound system can operate. The average speed of ultrasound waves in human tissue is 1,540 meters per second. And then this is actually a trick question. What is the average speed of ultrasound waves in outer space? And the answer to that is 0, because ultrasound cannot travel in outer space because there's no medium to travel through. So these are the various sound types by frequency range. So if you look up here, seismic waves are the waves basically that go through the earth. If we look at 16 hertz to 20 kilohertz is human speech and music. Down here, 20 kilohertz to 10 gigahertz is dolphins. But what we're really interested in here is our 1 megahertz to 20 megahertz, and that is diagnostic ultrasound imaging. There are various applications for diagnostic ultrasound. The first one is radiology, or it's also referred to as general imaging. And that applies to abdominal scanning, which would include gallbladder, kidney, liver, and spleen, and then something called small parts. Small parts is a generic term for a class of ultrasound exams that apply to superficial structures such as breasts, thyroids, testicles, and musculoskeletal applications. And then we have cardiology. Cardiology is the non-invasive evaluation of heart functions. What's interesting is that on the radiology side, it's called an ultrasound. On the cardiology side, it's called an echocardiogram. There is no difference between the two. It's the exact same machine, same function, same technology. It's just different terminology. And then we have vascular exams. And the vascular exams are used to detect blood flow and evaluation of the various blood vessels throughout the body. And it can be peripheral vascular or vascular throughout the abdomen. And then we have obstetrical and gynecological applications. And that would be for structures, fetal structures such as the heart, kidneys, and female structures such as ovaries, fallopian tubes, and the uterus. So how do we create these ultrasound waves? So essentially an ultrasound transducer has a piezoelectric element that generates this wave. And so this element will vibrate, creating a mechanical wave or an ultrasound wave. The wave then travels through a medium such as the human body, and then some of the energy gets reflected back towards the transducer. So the piezoelectric effect, not to get too technical, but it's the ability of materials to generate an electrical potential in response to mechanical stress, and vice versa. If you look at the breakdown of the word transducer, transducer means to take one type of energy and convert it to another. So with piezoelectricity, we're taking electricity and turning it into mechanical, or vice versa, mechanical into electricity. The vast majority of ultrasound transducers utilize a ceramic type material. Some use silicon, but there's some man-made materials that are being developed now by the manufacturers, a single crystal transducer array. So there's various materials that are utilized, but essentially they are a crystal in nature. So essentially what we do is we apply an electrical current to these transducers, and by applying electrical current to a transducer, it compresses that crystal. And once we compress that crystal, when we remove that electrical current, that crystal will then expand, which creates a mechanical wave. So with an ultrasound transducer, at least contemporary ultrasound transducers, we have a lot of crystals that comprise a transducer. Early transducers had single crystals, but contemporary transducers have up to 4,000 to 8,000 various elements. So each element is wired to the ultrasound system and is pulsed with an electrical pulse. The average two-dimensional transducer has 128 piezoelectric elements. And the diagnostic ultrasound imaging range of frequencies is between 1 and 20 megahertz. So if you look at this diagram, basically what we're showing is how an ultrasound transducer is fired. Now we're getting into a little bit of physics. So with an ultrasound transducer, the higher the frequency of the ultrasound wave, the less the ultrasound transducer can penetrate. And the lower the frequency, the deeper it can penetrate. So there's a trade-off. And this is where we, again, jump into ultrasound physics. So when we use a high frequency, we can only penetrate a few centimeters into the body. With a lower frequency transducer, the lowest frequency transducer, we can penetrate into the human body up to 24 centimeters. The other side of that equation is the higher the frequency, the higher the resolution that we get out of the ultrasound system. Conversely, the lower the frequency, the lower the resolution. So when we're performing an ultrasound exam, what we always want to do is use the highest possible frequency to get the diagnostic quality that we're looking for. These are the different ultrasound transducer formats. We have phased arrays, linear arrays, and curvilinear arrays. And all these different formats are utilized for different types of exams. And the analogy I can draw is various tools. I'm assuming that we have a lot of biomedical engineers on this call. and we all carry toolboxes, and we all have various tools for various jobs. Certain tools can do various jobs. We can use a screwdriver to pound in a nail, but it's not the right tool for the job. And so with ultrasound, we can use these various transducers to perform all different types of exams, but we really want to use the right tool for the job. And with a phased array transducer, you can see that the image format is pie-shaped. And so in the near field, we have a very small area. We have a pinpoint, and it goes out into a wedge area or a wider far field. That is typically used for cardiac exams, where we want to get in between the ribs or underneath the ribs and view the heart. With the linear array transducer, this is typically used for vascular or small parts type exams, where we have a fairly large near field and a uniform far field. If we look at our curved linear array transducer, this type of format is typically used for abdominal and endocavity work. And the nice thing about the curved linear array is that we have a really nice wide near field and a much wider far field, so we can get a lot of anatomy within the image area. So with our linear probe, this is the way a linear probe is fired. So an ultrasound system will fire the elements within a linear array transducer one at a time, very quickly, and create that linear type image. With a phased array transducer, we're firing the elements virtually simultaneously, but we're using variable timing on the pulses that are going to those crystals in order to steer that image. And so if you look at those two images, or those two graphics, the first graphic is we're firing the image straight on. The second graphic is we're timing the pulses going to those crystals to steer that image. Ultrasound systems have a variety of methods to focus the beam. With an ultrasound transducer, if you look at the top graphic up here, ultrasound transducers, the way the crystals are cut and shaped, have what's called a fixed mechanical focus. So if you look at this point here, this is where the ultrasound image is fixed mechanically based on the shape of this transducer array. Well, that's wonderful, and we create those arrays to focus in certain areas, but what if we want to look in areas that are outside of the fixed mechanical focus of that transducer? What we do is we can actually focus the ultrasound beam using what's called delays on either the transmit side or the receive side. And so on the transmit side, what we can do is we time when the pulse gets to the ultrasound array in order to create a certain focus. What we do is we create something called the mechanical lens. For those of you on this call that have eyeglasses, we all wear glasses to focus light on our eye at a certain point, depending on the deficiencies in the lens of our eye. Well, with ultrasound, we can do, rather than an optical lens, we can create a acoustic lens by timing these pulses and create different focal points with an ultrasound system. And so essentially what we do is we time these transmit pulses with these electronic delays and have these pulses hit the crystals at various times to create a certain focal point. We can also change our focus on the receive side. So using the same delays is we can change how we receive these reflected energies to create a different type of focus. So if you look at this image here, essentially what we're doing is we receive the reflected sound waves from the body. They come back and they hit these crystals at various times. And what we use is a delay to get all these received signals in sync, so they're all coming back at the same time. And so what we're doing is we're controlling the delays on these received signals to ensure that the system is processing all these signals at the very same time. Basically the way an ultrasound system works, and it's really cool and very simple at the same time, is the ultrasound system generates high voltage pulses. These pulses go through the transducer cable, they hit the crystals then vibrate, creating a mechanical wave. The wave then goes into the body and is reflected off of various structures and then comes back at various intensities. So a very dense structure will reflect a higher energy back as opposed to a very soft structure which will reflect a low energy back. And so what the ultrasound system does is it looks at those signals coming back and it assigns a shade of gray to those signals. And so if it's a very high energy signal coming back, it's a very bright shade of gray or almost white. If it's a very low density signal coming back, it assigns it a dark shade of gray or almost black. And we have all these various shades of gray, and so all these signals coming back, we assign different shades of gray to, and that's how we get our ultrasound image. So if you look at this image here, all these bright white areas here are bone, and bone is very dense, and so it reflects back a very high energy wave. If you look at this area here, this is amniotic fluid. And amniotic fluid is not dense, and so it reflects back very low, and so the ultrasound system is assigning a very dark black or either or dark shade of gray to those echoes. So let's talk about tissue interactions. Tissue interactions, there's 5 different tissue interactions when we send sound into the human body. So there's the first one is transmission, second one is reflection, third one is scattering, the fourth one is attenuation, and the fifth one is refraction. So transmission is important. When we send sound into the body, we want the sound to reflect off of structures, but we also want to go through structures. Otherwise, we would only see the first layer of tissue that the sound is hitting. All that sound would reflect back, and we would just see the superficial tissue barrier. What we want to see is we want to see through the body as well. So we want to see what's at 1 millimeter and also what's at 24 centimeters. So transmission is critical. And then we have reflection. Again, reflection is critical as well. These sound beams have to be reflected back to the transducer to vibrate those crystals so the ultrasound system can look at the various intensities and assign shades of gray. And then we have scattering. Scattering is when the ultrasound beam goes into the body and is not transmitted or reflected. It just breaks down and reflects in all different directions. And it's a very weak signal, and most scattering does occur with red blood cells. But scattering does occur when sound hits bone or sound hits air. Ultrasound, conventional ultrasound, does not transmit through bone or through air. And there's very specialized applications where we can transmit through bone. There's something called transcranial Doppler where we can actually penetrate ultrasound through thin bone, but that's a very specialized application. Attenuation. As ultrasound goes through the body, it is attenuated or it breaks down. It weakens. And that's just a natural function of the ultrasound beam. And there's absolutely nothing we can do about it. That's something that we factor in when we process the ultrasound beams coming back. So ultrasound attenuation effects. Ultrasound attenuation, it can't produce heat, and it is used for non-diagnostic treatments. What we're talking about today is diagnostic ultrasound. There's also therapeutic ultrasound where the device will concentrate lower frequency ultrasound on a certain area of the body, which will create heat. For diagnostic ultrasound, that is an undesirable effect. We do not want to do that. And so the AIUM, the American Institute of Ultrasound and Medicine, has guidelines on how much heat we can generate. Essentially what we want to do is we want to generate as little heat as possible while we're scanning a patient. And there are limits that the FDA has set on how much mechanical energy we can generate into the body. Refraction is when we send sound into the body and it hits an interface and it generates an off-axis reflection or transmission. So we can use refraction to our benefit. We can enhance image quality by using our acoustic lens that we talked about earlier in order to focus that beam coming back and create a better image. So when we talk about image quality, there's a lot of different factors that go in image quality. And for those of you on the call that are doing ultrasound service or will be doing ultrasound service, there's a lot of things that we need to know about image quality. Image quality is a very broad term, but what exactly does that mean? So we're going to talk about detail or spatial resolution, image uniformity, contrast resolution. We're going to talk about temporal resolution or frame rate, dynamic range, spatial discrimination, and bandwidth. So let's talk about axial resolution. So axial resolution is the minimum separation between two structures along the path of the ultrasound beam. So if you look at this graphic here, we have two very small structures along the length or the distance, the path of the ultrasound beam. So how good, basically what we're asking here, is how good is this ultrasound system at distinguishing between two very small objects that are very close together along the path of the ultrasound beam. Now we have lateral resolution. Lateral resolution is the ability of an ultrasound system to separate two very small structures very close together that are perpendicular to the ultrasound beam. So if you look at these objects here, you see here these two objects would be seen as one structure. Down where the beam narrows, where we have our focus, we would be able to distinguish these very two small structures. And down here, where we start losing focus, we would see these two objects as one structure. This graphic over here on the left is actually, it's a graphic of a tissue mimicking phantom. This particular phantom is called the ATS Model 539. This is a phantom manufactured by ATS Technologies. It's a wonderful phantom. For those of you that are looking for a phantom, I highly recommend ATS phantoms. They're very cost effective and they're extremely durable. They never need to be calibrated and they will virtually last forever, even with physical abuse. They're good with temperature extremes. They can handle very hot and very cold temperatures without going out of calibration. They can be dropped and survive through it. We do distribute this phantom, and so if anybody is looking for a phantom, we can get you a great deal on the ATS line of phantoms. But what you're seeing over here is a graphic of this phantom, and these objects here represent cystic structures. These objects over here are pins, and when we scan these phantoms, what we want to do is we want to look at, can we distinguish all these different pins with our ultrasound system? Can we separate those with the ultrasound system, or do they appear as one structure? Transverse resolution is, if you look at this graphic here, basically we have our x-axis, which is left and right, our y-axis, which is up and down, and this would be our z-axis, which is our depth. So transverse resolution is, can we distinguish between two structures that are side by side along the ultrasound beam? And then we have contrast resolution. Contrast resolution is the ability of the ultrasound system to differentiate between various structures of very similar densities. And so there are various things that happen with the human body. For example, there's certain masses that are grown in the liver, where they take on a very similar density to surrounding tissue. And so when you scan the liver, you can kind of see the masses, but you're not sure. And so with a really good ultrasound system, a really good ultrasound system, a very sensitive one, has the ability to differentiate between two tissues of extremely similar densities. So if we look at our ultrasound phantom again, going back to our ATS 539 phantom, these grayscale target groups, what we're doing here is when we scan, when we place a transducer on the top of this phantom, is can we see the different objects here that are only 3 decibels apart in intensity. And again, a good ultrasound system can differentiate all 6 of those objects. A not so good ultrasound system cannot. Now we're going to talk about different ultrasound modes. Contemporary ultrasound systems have a variety of different modes where they use ultrasound for different diagnostic purposes. The first thing we're going to talk about is Doppler. Doppler is utilized in various ways on contemporary ultrasound systems. A great analogy is a police officer with a radar gun. Police officers utilize radar guns to determine how far, or not how far, but how fast a car is going. So what they do is they send out a beam and they bounce it off a car and they get it back, and they can judge by the amount of time it took for that beam to go out and back and the change in frequency. They can tell you how fast you were going and in which direction you were going. So another good analogy is when we're sitting at an intersection and we have to stop for a train going by, and that train is blowing its whistle approaching the intersection. That whistle starts with a very high pitch, and as that train passes by, you can hear that pitch going down, because as the train is coming towards you, essentially what that train is doing is it's compressing the wave, the beam of that sound wave, creating a higher frequency. And as it goes away from you, it's essentially dragging out that beam or creating a longer wavelength, which is a lower frequency, which is a lower sound wave. So if the source is moving towards you, the frequency goes up. If the source is moving away, the frequency goes down. So what we do is we use Doppler to evaluate blood flow. So we send a sound beam into a blood vessel or a heart chamber, and we bounce that sound beam off of red blood cells. And we read the frequency of that beam coming back. And so we know the frequency of the sound wave that we're sending out. The system is generating a certain frequency. We'll call it, in this case, we'll call it 4 megahertz. And so if we send out a 4 megahertz beam and we get that beam back, if it's higher in frequency, we know that blood is coming towards us. If it's lower in frequency, we know that blood is moving away from us. And by the frequency shift, we can actually tell how fast that blood is going, and then we assign a certain shade of gray, and we map it using this scale. And so we can tell exactly how fast that blood is going. And so this is a very good Doppler signal. If you look, we can tell exactly how fast this blood is going because we have a little scale over here. And you see that we're at 50 centimeters per second here. So this is almost 100 centimeters per second. And we have a nice clean area underneath this wave, which tells us there's not a lot of turbulence in this vessel. Turbulence in a blood vessel is bad. And that means we have a variety of different frequencies. That means that the blood is not flowing clearly. It's hitting some kind of structure within that vessel and creating a bunch of different frequencies. Typically, in this particular image, we're looking at a common carotid artery. If there was some plaque here, if we had a big piece of plaque here, the blood cells would be hitting that plaque and causing all kinds of turbulence, which would create all kinds of different frequencies down here. So direction of flow in a blood vessel. When we're using pulse wave Doppler, we cannot hit the blood vessel at 90 degrees or perpendicular. We would have no Doppler shift. And so with an ultrasound system, we use timing to steer this ultrasound beam. Optimally, we want to be 60 degrees on the vessel. That is the optimum angle, but we can, that's in a perfect world. The ultrasound sonographer will try and adjust that beam to 60 degrees. They'll get close, but there's tools that the ultrasound system utilizes to compensate for angles that are not 60 degrees. Aliasing. Aliasing is something that, for those of us who are doing service, we want to be aware of. Aliasing is what happens is when our Doppler sample rate is not high enough for a high frequency shift. And what you'll see is this here. So essentially you have your pulse wave, your graph, where the signal is being cut off at the top here, and you can see where it's being wrapped around. And so basically if you look, if we were to be able to lower this baseline here down to the bottom, we'd see the entire signal, but we don't have that. So basically we're cutting off the top of the signal, it's wrapping around. This is called aliasing. This is not a malfunction. I spent 25 years as an ultrasound service engineer, and I can't tell you how many service calls I was brought out on where the customer said, there's something wrong with my Doppler, and I've gone in and I've seen this. This is an adjustment of the machine and not a malfunction. For those of you on this call, we also present this class or seminar called Ultrasound Applications for Service Engineers. It's a class that I wrote with my wife, who is actually a registered sonographer, and the class covers essential clinical applications for service engineers. So being a service engineer, when you go into a call and it's an image quality call and the sonographer says, well, my image is grainy, yucky, mushy, contrasty, I have aliasing, all those different things, this class covers what those terms mean and how to adjust for that. And it's a fantastic class. I don't know of any other organization out there that covers clinical applications for service engineers. So if you have the opportunity, we're teaching another webinar. I don't know the date, but email me and I'll get that date back to you. I welcome you to sign up for that webinar because it's really cool, and we do talk about ultrasound clinical applications and go into depth on some of these anomalies and images. This is another anomaly that we have called mirroring. And basically what this is, it's the Doppler signal where we have the exact same signal above our baseline as below our baseline. And this is a malfunction within the machine. There's another type of Doppler called aux continuous wave. This is also referred to as blind Doppler. And the reason it's called blind Doppler is that we're only doing Doppler. We do not have a two-dimensional image. This is what a auxiliary continuous wave transducer looks like. It's very small. It basically looks like a pencil. It's also called a PEDOF probe, P-E-D-O-F-F. And then we have something called steered continuous wave. Steered continuous wave is typically used for cardiac applications, and this is a Doppler where we're doing Doppler while we're viewing the heart. And so we have a nice 2D image, we have a color Doppler image, and we have a continuous wave Doppler image down here. Now we get into color Doppler. Color Doppler, when it first came out, it was referred to internally with some of the manufacturers as Doppler for dummies. It's a very, very poor term. But what color Doppler does is it presents blood flow in a graphic, a color graphic form. If we go into our previous Doppler forms, the continuous wave and the pulse wave, it is actually a graph, and it takes a very highly trained individual to read that graph and know the dynamics of that blood flow. With color Doppler is much easier to read. Blood going towards the transducer is one color, blood going away from the transducer is another color. Higher velocities are lighter and lower velocities are darker. And so if you look at this image here, this actual image is an umbilical cord. What we're looking at is the umbilical cord in an expecting mom, and we actually have 3 different vessels here. And so the red and orange and yellow is blood going towards the transducer, and the dark and light blue is blood going away from the transducer. And so what we're doing is we're sending sound waves into the blood vessel, and we're assigning colors based on whether the blood's coming towards us or away from us and how fast the blood is going. This particular image here is the hepatic veins within the human liver, and you can see that this graph over here on the left, we have red up above and blue down below. So red is coming towards the transducer, blue is going away, and the slower velocity reds are very dark. The higher velocity reds are very light, and with the blues, the very slow velocities are dark blue, and the faster velocities are a lighter blue, going towards white. So what we do is we put a color box on the image that we're looking at, and we tell the ultrasound system, I want to interrogate this particular part of the body. And bear with me, I'm going a little faster than I normally go. This seminar normally takes an hour and a half, but in the interest of time, I know we have a lot of people who are very busy. We compress this down to an hour, so I'm going to kind of skip through. We will send all of you this slide deck when we're done. And again, you all have my email address, and I'll send it again at the very end. But you're more than welcome to contact me with any questions or any additional material that you would like. So the image that we're looking at here is actually the kidney, and you can see all the different velocities within the kidney and all the various directions that blood is going. This particular image here is a common carotid artery, and this is called a bifurcation, where the blood goes in the external carotid artery to the face. And then this lower vessel is the internal carotid artery, which feeds our brain. We can also have aliasing in color Doppler as well. If we do not adjust the system properly, what happens is the velocity within this vessel exceeds where we have the system set at. In this particular case, we have the system set at 6 centimeters per second. We are going faster than that, so what's happening is we're exceeding this velocity and we're actually wrapping around to the bottom. So if you look at this vessel here, we're going too fast and we're actually exceeding where we set the system, and we're going to the light orange and we're going down into the turquoise. This is called aliasing. Again, this is not a malfunction of the machine, this is merely a setting. So what defines a good color Doppler image? Well, we want the color to fill the entire blood vessel. We want the walls clear of any color. We want adequate frame rate, and frame rate is how fast the system is scanning. And we want good spatial resolution, which means we have small color dots or pixels. If you look at this particular image, this is a poor color Doppler image. And the reason it's poor is that if you look up here, the color is bleeding outside the wall of the vessel. That we do not have good color fill, and we have a lot of pixels. So this is a very poor color Doppler image. Now we have something called Power Doppler. Power Doppler is really cool. It came out some time ago. All the manufacturers have it. And that's one thing about these different modes. I'm going to use different terms like Power Doppler and Power Doppler Angio. All the manufacturers have these different things. They just use different terms so they can claim that, oh, we're the coolest, we're the best. But all these different Doppler modes and all these different imaging modes are utilized by all the major manufacturers. This power Doppler ultrasound, it's also called PDI, it's called color power angio, but it's a type of Doppler that will give us energy of blood flow. The good news is it shows where we have flow, and it's extremely sensitive. The bad news is, the trade-off, is that it does not give us velocity or direction information. So if we're doing something where we're just looking for presence of flow, for example, if we have, say, an elderly person and we're looking in their extremities, do they have flow in their extremities? Or it's particularly used in testicular exams. So if a man has something called testicular torsion, where the blood flow to the testicles is cut off, we want to know, is there any flow at all? We don't really care how fast it's going. We don't care what direction it's going. Is there flow or is there not flow? So color power Doppler is utilized for those types of exams. So again, it's extremely sensitive. It tells us if there's flow, but it just doesn't tell us how fast it's going or what direction. There's another type of imaging mode called sono-CT imaging. General Electric calls it compound imaging, or crossbeam. Siemens calls it compound imaging. But really what it is with conventional imaging, if you look on the left, we send a beam of ultrasound energy into the body, it reflects off a structure, and it bounces back. With compound imaging, what we're able to do is we're able to steer the beams going into the body in different directions. And the cool thing about that is it's like a CT exam. The reason CT creates such a really nice, sharp image is because we hit the body from various angles. With sono-CT, or compound imaging with ultrasound, we're doing the same thing. We're hitting a structure within the body from various angles. So if you look at this image here, oh, let me back up. I don't have an image, I apologize. But what it does is it reduces angle-generated speckle noise artifacts. It improves our contrast resolution. It also makes the image very smooth. And it has been shown to improve diagnostic outcomes in the vast majority of patients. So it's a really cool technology. In fact, I'm going to go back to this image for just a moment. For those of you who are out doing PMs or in front of ultrasound machines, if you get in front of an ultrasound machine, turn on compound imaging or sono-CT or crossbeam, depending on the manufacturer, turn it on, and then take a coin or a paper clip or something along those lines, something metallic, and put it on the face of the transducer, and you can actually see these various beams in the image area. It's kind of neat. Harmonic imaging. I imagine we have about 100 attendees today for this webinar. I imagine there's at least 10 or 20 people on this call that are musicians. And so if you're a musician, you understand harmonic imaging. Harmonic imaging is, for every sound wave that we have, it has a harmonic. And a harmonic is either twice that frequency or half that frequency. So for example, if I have an ultrasound beam that is 4 megahertz, the harmonics of 4 megahertz would be 8 megahertz and 2 megahertz. It would also be 16 megahertz and 1 megahertz, 32 megahertz and 500 kilohertz, and so on. So it's always twice or half our primary frequency. And where we use that in diagnostic ultrasound, it's kind of cool. What we do is we send out an ultrasound beam. And if you look at this graphic here, we're sending 2 megahertz into the body. But what we do is we filter out that 2 megahertz coming back, and we listen for 4 megahertz, which is a harmonic of 2. And the reason we do that is for certain types of patients and certain types of exams, it gives us a little bit cleaner image. So for example, if you have a heavier patient and we're trying to do their gallbladder, harmonics works wonderfully in cleaning out that gallbladder. It's especially effective with structures that have fluid in them. So if you look at this particular image here, what we have is we have vessels within the liver, and you can see the harmonics over here, how it really cleans up the image here. Panoramic imaging. Panoramic imaging allows us to scan, to do essentially a sweep through the body. So I can use something if I'm doing something called vein mapping. I can actually map the veins in my arm by taking the transducer, placing it up by my bicep, and enabling this panoramic imaging, and I can slide the transducer down my arm, and the ultrasound system will piece that image together and create this image. And again, bear with me, I'm going to skip through some of these slides in the interest of time. 3D imaging. 3D imaging, it's been out for quite a while. The technology has gotten absolutely amazing. As I mentioned earlier, my wife is a sonographer. Her specialty is high-risk obstetrics, and so she specializes in doing multiples. And so she does twins and quints and quads and all that, and she sends me these three-dimensional images all the time that are absolutely amazing. With three-dimensional imaging, what we're doing is we're essentially doing a sweep through the body and reconstructing that image to create these wonderful 3D images. This particular image here, obviously it's very clear. We can see baby here. The technology has actually gotten better even over the last year or two, where you can see exactly what your baby's going to look like prior to baby meeting the world. So we have 3D imaging. Now we also have something called 4D imaging. And all 4D imaging is three-dimensional imaging with the element of time. And so we're doing real-time 3D imaging. So rather than doing a sweep through the body and reconstructing that image, we're actually doing real-time four-dimensional imaging. And with contemporary ultrasound transducers and faster processors and some really cool technology that the manufacturer are using these days, we can do real-time four-dimensional imaging with real high frame rates. This is actually an image of a heart valve and chamber. We're now using four-dimensional imaging or real-time 3D ultrasound imaging in the human heart. There's a couple different types of four-dimensional imaging transducers. One is a mechanical transducer, where the crystal array is inside this dome that's filled with a high viscosity oil, and the transducer array will sweep back and forth rapidly as we're scanning the patient, creating this image. There's also solid-state four-dimensional imaging transducers where we use different timing to create these four-dimensional images. So what you're seeing here is a four-dimensional cardiac image. And for those of you on this call, and this actually applies to the clinical applications webinar that we do, but I want to take a quick tangent here and encourage you, when you get in front of an ultrasound system, please take a transducer, put some gel on it, lift up your shirt, and start probing your abdomen, moving around, pushing buttons. The best way to learn how to fix ultrasound machines is learning how to use them. You're not a complete ultrasound repair technician until you actually understand how to utilize ultrasound. And it's an amazing technology. I've been doing this for 30 years, and it's extremely rare that I get in front of an ultrasound system where I do not put gel on the face of that probe, lift up my shirt, and start scanning, because it's just really cool to be able to go through your abdomen and do your carotid. And over time, you will develop the skills. You'll never be a sonographer unless you actually go to school for 4 years. But you can pick up a lot of that technology, a lot of the terminology, a lot of the skills to learn how to use these things. So now we're going to talk about the basic building blocks of an ultrasound system. So again, the manufacturers, they have different terms for how their ultrasound systems are constructed, but they're all the same. And the analogy I use, I always go back to automobile analogies, because everybody understands automobile analogies. So if you have a Chevy or a Mercedes or an Infiniti or a Volvo, they all have engines, they all have transmissions, they all have rear ends, they all have different options. They're all the same. They call them different things. They're constructed in slightly different ways, but they all have the same functions. So with an ultrasound system, we have something called a front end or scanner, a coherent image former, or an acquisition subsystem. All really cool, fancy terms, but they're all the same thing. And then we have a back end, or also a scan converter, DIMAC workstation, or platform subsystem. Again, same thing, different names. And then we have power subsystems. So these things, the front end, the back end, they have to be powered somehow. So we have power subsystems. And then we have software. We have an operating system and ultrasound application software. All contemporary ultrasound systems have this. They have an operating system. Typically it's Windows. There are some hybrids out there. If you look at the GE Vodisance, for example, they use a hybrid of Linux and Windows, but the vast majority of ultrasound systems are running Windows with the manufacturer-specific ultrasound application software layered on top of that. And then we have our ultrasound transducer, we have a user interface, and then we have our display. So I'm going to skip through this really quick because we're kind of running up against the clock, and I want to leave a little bit of time for questions. And so this is a basic building block for an ultrasound system. So at the very bottom, we have our AC input box. So we got to get power to the system. And then we have our two different power supplies, high voltage and low voltage. We have our front end, and our front end is responsible for creating the image. How is the image created? And that is, we create the beam, we hit the transducer with ultrasound or with electrical pulses. Those pulses go into the body, they come back, they're reflected. We get a reflection back. How do we interpret that? We have to analyze that. That's all done in the back end, the analysis. And then we have a display. We have to display it on the screen. We have the user interface where the operator will tell the machine what to do and how to do it. We have DICOM, which is the language we use to transmit our images. We have our software up here, and then we have all our various options. And ultrasound systems are like automobiles or like a pizza. When you order an automobile, you order a pizza, you order the basic model. So I want a large pizza, and then you start ordering toppings. Your toppings are essentially your options. Same with ultrasound systems. Ultrasound systems have a variety of options that you can add to it, and that's what we see up here. So a generic front end of an ultrasound system has our probe interface, and that's the board or the section of the system that you plug your ultrasound transducer into. We have a transmitter, and that's the device that generates our high voltage pulses, which hit the transducer and send the wave into the body. And then that wave comes back, it hits the transducer, generates these small electrical pulses. Then we have a receiver, which are highly specialized amplifiers, which amplify the echoes coming back. And then we have a beamformer, which starts processing these echoes coming back into something that we can view. And then we have a front-end controller. The front-end controller's job is to tell the front end what to do and how to do it. So for example, if we have a 50-pound child come in for an abdominal exam, we're going to set up the system in a certain way. And then the patient right after that is a 350-pound adult, and we're doing their abdomen. Totally different setup. That front-end controller will tell the system, hey, wait a minute, we got a totally different type of patient. We have to send out different types of signals, different intensities. We have to focus in different areas. That's the front-end controller's job. Now we have our back end. And our back end, its job is to take all these received signals and create an image that the human eye can understand. And in the vast majority of contemporary ultrasound systems, this back end is a computer. So if you look at this, we have a master controller or a CPU, we have image memory, we have a video card, we have our peripheral interface, which is where our control panel that the sonographer utilizes to give commands to the system, it comes into the computer and it tells the computer what to do. So I'm going to skip through this. And again, you will all be getting this slide deck when we're done. And I want to show you the block diagram for a couple of contemporary ultrasound systems. And bear with me for just a moment. So this is an Ultrasound Sequoia, a little bit older system, but this is what the front end looks like. And so we have transmitters. They generate these high voltage pulses. Those pulses go to the transducer interconnect board. They go out to the transducer. They send the signals into the body. The signals reflect off structures. They come back in, and now they go over to receivers. These receivers are high gain amplifiers, and they amplify these signals. These signals then go to something called a beamformer. The beamformers start adding all these different channels together, and then they go back to a controller board where they go into the scan converter, and the scan converter processes those returned echoes and creates this wonderful image that we see on the screen. This is a GE Voluson. The GE, let me skip back. The GE Voluson, a little bit different architecture. So we have our main power supplies. We have our beamformers that send the signals into the body and out of the body. We have our CPU, and we have our back end, which processes all these signals. This is a GE Vivid 7. Again, we have our front end, our back end, and our display. And this is one of the most common systems out there, our Philips IE22, IE33. We have our front end, we have our channel boards. Our channel boards of transmit and receive. Our front end controller tells them what to do. Our name board is used for initial processing before everything goes back to the UMB or the EMB for processing, and everything's displayed on our screen up here. And then we have our power supplies down here. And now we have a bunch of acronyms, which I'm not going to get into. Again, I will send this presentation on to all of you. We have a couple of minutes left. Please use your chat box to ask any questions, and I'll be happy to answer them before we wrap this up. Well, either I did a really good job or everybody's already left me, but I don't have any questions coming in. So I want to thank you all for attending this seminar. And again, please feel free to email me. And with any questions or any additional content that you would like that applies to this webinar or anything else that we present at Conquest Imaging. I wish you all a wonderful day.